So what's the best we can do in terms of speed or performance of sorts? How fast can we have our sorts be? So we'll start with an argument about trivial lower bound, just kind of using kind of a common sense description of how our programs are working. So consider that we have some sort of an array with elements in it, 8, 2, 21, 5, and so on. And we've got at least one unknown element. I think we could make a reasonable argument that we have to look at each element in this array at least once before we can figure out where to put another element. So since we have to look at each element once, we could make an argument that we have to have at least an omega of n as kind of our lower bound. So we'd expect almost any sort to take more than n operations for n units of data. Of course, we're making an assumption here that our computer only does one thing at a time. So parallelism, doing multiple simultaneous operations, is considered in other courses, but we won't be considering it here, or at least not now. Okay, so as we already saw, there are several different ways to classify sorts. So one of the ways we can classify a sort is whether it is possible to do it in place or not. So by in place, what we really mean is whether it's possible to do it with a constant amount of memory, or whether the memory depends on the amount of memory used somehow depends on the amount of input data or the number of steps it has to go through. Another way of classifying sorting algorithms is whether they're a comparison sort or a non-comparison sort. So in this module, we'll look at both. But up until now, every sort we've talked about is a comparison sort. So what this really comes down to is whether the sort is somehow dependent on the notion of one thing coming before another. Or you can think of that with the less than operation when talking about numbers. So in discrete math, this is really about having some sort of a relation that imposes a total ordering. So we've usually been sorting things into ascending order, which uses either the less than or equal to operation. But everything we're talking about is equally valid if you only had greater than or equal to. So as long as you have some way of doing comparisons and establishing the relative order of one item to another, it would be considered a comparison sort. So when we're working with Java objects, there's a specific interface, the comparable interface, provides a compare to method that essentially allows us to do this, to identify the relative ordering of one object with respect to another. Okay, so let's try and pin down the omega, the lower bound, for comparison sorts. So first of all, let's just do a quick overview of some of the terms that we need in order to identify this. So we'll assume that we have n items that we want to sort. So let's think about how many different permutations we might have of n items. So if you've taken a class that covers basic counting and probability, you've probably already reviewed this. If you had a discrete math class, you've already looked at this. So the basic idea is that if we've got n items and we're trying to put things in a particular order, the thing we could place first, we've got n choices of. And then once we've put something in the first spot, we've got n-1 choices for our second spot, and so on and so forth. So the total number of possible orderings would be the n items for the first choice times the n-1 items for the second choice, and so on and so forth. So the total number of permutations can actually be expressed with factorial, n times n-1 times n-2, and so on and so forth down to 1. Okay. So as an example, imagine that n is 3. So we would have 3 factorial, or 3 times 2 times 1, otherwise known as 6 different orderings. So if our items were A, B, and C, one ordering would be A, B, C. We could also have ACB, BAC, BCA, CAB, CBA. So those are 6 possible permutations of 3 items. Okay, we could also apply numbers to these. We could refer to one of them as permutation 0, another as permutation 1, 2, 3, and 4, and 5. So we could have a total of 6 different permutations. So we could give some sort of numbers or names to them. Now, imagine that if we could identify the particular number or name, that we have some sort of a magic oracle or a function that if we say, hey, I've got permutation 3, it can automatically put them in the right order in constant time. So imagine that if we had this magical oracle, that would change our sorting task from reorganizing data to just identifying which permutation we had. So I'm using this as kind of an argument to simplify our description of time complexity and to focus on just the comparisons that need to take place. Now, in reality, everything we're talking about applies to all sorts, even if we're including the time to swap elements around. But this will allow us to just focus on just the idea of identifying the ordering of items rather than the effort needed to swap them around. Okay, so if all of our work was just identifying which permutation we had, and we're just using comparisons like less than, we'll try and identify our time complexity. But we're going to assume that we've got the worst case input data. As we've already seen, sometimes a sort that's considered to be relatively poor, like insertion sort, does relatively well if the data is suitable for it in a particular way. We'll assume that our sorts always have the worst case data for that particular sort. So we'll come up with a lower bound, a big omega, that basically tells us the lower bound for the worst case possible data. Okay, so we're going to be deciding which permutation we've got given a set of data, x1, x2, x3, up to xn. So the way we're going to do this is by doing comparison. So we could compare two elements of this collection of data, and I'm just going to use some subscripts to refer to them kind of arbitrarily. So the ith element of x is being checked to see if it's less than the jth element of x. When we do that comparison, we'll end up with two choices. Either it's less than or it's not. So we could actually think of this as kind of a branching situation where we've got two options that come off of this decision. And then following that, we might make another decision. Once we know whether the ith item is less than the jth item, maybe we'll see if the kth item is less than the lth item. Or if it was not less than, maybe if we go on the right side of our little branch here, maybe we'll check some other pair of items. Okay, so what's happening here, or what's depicted here, should look kind of familiar. We're basically using a tree representation to represent a sequence of several different decisions we need to make. So in this tree representation, internal nodes represent comparisons between individual elements. So each step through this tree basically corresponds to one comparison. And just like we've done all semester, we're going to assume that a comparison is a constant time operation. Okay. So that kind of represents the idea of time. Okay, so we've also got the leaves on our tree at the very bottom. So here it's depicted with ABC representing one of the possible permutation. So leaves of this tree represent a specific permutation. So the entire set of leaves across the bottom of this tree represents a permutation. All of these internal nodes represent a comparison. And the path down the tree from one node to another basically represents the number of steps or the number of comparisons we need to do in order to identify a specific permutation. Okay, so the height of the tree basically represents the number of comparisons that we have to do. And again, we're kind of simplifying our argument and just focusing on the amount of work we do in comparisons and ignoring the amount of time it would take to actually swap elements around. So what's the minimum height possible? That kind of corresponds to the amount of time that may be necessary for some set of input data. So let's do kind of a quick refresher of heaps and some of the things, the terminology and concepts we were talking about when we looked at heaps. So if you remember, we looked at this idea of kind of a complete full binary tree, and it has the most nodes possible for a given height. So that's kind of a dense tree that kind of forms this perfect triangle. In this case, I'm going to assume that it is truly a perfect triangle, that the bottom layer is as full as it could be. Okay, so if you remember, these trees kind of build from left to right, top to bottom, and we establish some relationships for the number of nodes. So for a tree of height h, it has 2 to the power of h between 2 to the power of h nodes and 2 to the h plus 1 minus 1. But what we're really interested in here is the number of leaves, because the number of leaves kind of corresponds to the number of possible permutations. So if you remember our little example tree, looks something like this, had all the nodes, and kind of the bottom layer represents the permutations, and we had n factorial permutations. So if we have one of these kind of complete dense binary trees, the number of leaves in the tree is less than 2 to the 8th, less than or equal to 2 to the power of h. Okay, so our overall tree. Let's start putting some of these different details together. So a complete binary tree is the best case for a particular height. Okay, so we might have a tree that's not as dense as a complete binary tree. And maybe there's some gaps where nodes are missing, and it has an actual higher height. So if we were to remove any of these nodes that are kind of on the interior of our tree and move them down lower, our height would actually go up. So again, the basic idea here is that a complete binary tree is really the best case for the height. If it's not a complete dense binary tree, the height will even be greater than this, and we're trying to come up with a lower bound. So we're just trying to if it's greater, that's okay. We're just trying to come up with something that is as low as it can reasonably be. Okay, we've also identified that the leaves will represent our different permutations of our data, and we'll have n factorial leaves. So the number of leaves is less than or equal to 2 to the h for the complete binary tree, and we've got n factorial leaves. And the overall height will be the number of comparisons needed for some worst case set of input data. Okay, so we've got this complete full binary tree. N factorial leaves is less than or equal to 2 to the power of h. So we're going to go ahead and solve for h. So we'll take the log of both sides here. And we'll simplify a little bit. Log base 2 of 2 to the h can be simplified to just h. So we now have an equation expressing the number of permutations versus the height. Or we can read this backwards, and we can say that the height must be greater than or equal to the log base 2 of n factorial. Okay, let's continue to manipulate this just a little bit further. So let's try and continue to work with this until we get something that looks like a familiar form. So we've established that h is greater than or equal to log base 2 of n factorial. So let's do a trick. Let's try and find something that's even smaller than log 2 of n factorial. So another way of saying that is we want something that log base 2 of n factorial is greater than. And then also because this is a transitive relationship, h will also be greater than this other thing. Okay, so we could think of the log base 2 of n factorial as the log base 2 of n times n minus 1 times n minus 2, etc., down to n over 2. And then it will continue decreasing that after that down to n over 2 minus 1, down to n over 2 minus 2, and so on, down to 2 and 1. Okay, the important part about this here is we could think of having about half of these terms that are greater than or equal to n over 2. Okay, and then we would have the other half of the terms that are less than that. So we can come up with something that is actually smaller than this pretty easily just by focusing on that first half of the terms. So half of the n over 2 terms are larger than n over 2, but then they'd be multiplied by something that's greater than 0. So we could argue that log base 2 of n factorial is greater than or equal to log base 2 of n over 2 to the power of n over 2. Okay, so again, this has several terms here that are greater than n over 2, and also some of them that are less. And so this overall expression will be smaller than n factorial. Okay, so we can then adjust the relationship there just a little bit further, take the exponent out of the log, and it'll be a coefficient on the log. Okay, now we can put all of this together. So we've already established that the height will be equal to or greater than log base 2 of n factorial. So the number of decisions we have to make has to exceed that. And now we've established that log base 2 of n factorial is greater than or equal to n over 2 times log base 2 of n over 2. Okay, and so we can actually kind of drop that middle expression, just simplify a little bit. So h has got to be greater than or equal to n over 2 times log base 2 of n over 2. Or we can just simplify this and, of course, drop the coefficients that are unnecessary, and we can say that h is in big omega of n log n. Okay. So, big picture here. In the best case, we have at least order n operations. We have to look at all the data at least once to know if it's even sorted. So we've also established a big omega, a lower bound on the worst case data. So at least for comparison sorts are big omega of n log n.